Now, in this lecture, we'll find out the radius of a circle using two different methods. In the drawing, we have a circle. We know that the center of the circle is at this point, point O, and line segment AB equals to 6 units, line segment AD equals to 18 units, line segment BC equals to 13 units. This angle PAD equals to 90 degrees, and this angle ABC, it is also equals to 90 degrees. Our mission is to find out the radius of this circle. So first of all, we'll make a construction, which is to say from point C we will go perpendicular on AD. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and AD is E. By doing this construction, we created here quadrilateral ABED. Inside quadrilateral ABED, we have 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3, 270 degrees, plus this fourth angle. In total, they must be equal to 360 degrees. So in order to complete the sum of the angles in this quadrilateral to 360 degrees, this angle must be equal to 90 degrees. This is according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So actually, inside quadrilateral ABEC, we have 4 right angles. Therefore, this quadrilateral, we will relate to it as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC. But AB equals to 6 units, therefore EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that BC equals to AE. But BC equals to 13 units, therefore AE must be also equal to 13 units. What is the length of line segment ED? It's very easy to see from the drawing that the length of ED is AD minus AE. AD minus AE is 18 minus 13, that is 5. So ED equals to 5 units in its length. In the next step, we will join points D and C together by a straight line. By joining points C and D, we created the green right triangle EDC. So we will implement the Pythagoras theorem on the green right small triangle EDC. Here, by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the green triangle EDC is DC, therefore the square of the hypotenuse is DC squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to CE squared plus AD squared. So DC squared, that is the square of the hypotenuse, equals to CE squared. CE equals to 6 units, therefore CE squared equals to 6 squared, that is 36, plus ED squared. ED equals to 5 units, therefore ED squared is 5 squared, that is 25. So in conclusion, we found out that DC squared, that is the square of the hypotenuse of the green triangle, equals to 36 plus 25. 36 plus 25 is 61. So we found out that DC squared equals to 61. We will take out all of this equation and we get that DC equals to the square root of 61 units. Here, the hypotenuse DC equals in its length to the square root of 61 units. In the next step, we will join points P and D together by a straight line. We're joining points B and D, actually created here, the right triangle ABD. So we will implement the Pythagoras theorem on the right big green in the right big triangle ABD. Again, by PT is a measure for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle ABD is BD, therefore the square of the hypotenuse is BD squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AB squared plus AD squared. In conclusion, according to the Pythagoras theorem, in the right triangle ABD, BD squared equals to AB squared plus AD squared. So BD squared, that is the square of the hypotenuse of the right triangle ABD, equals to AB squared. AB equals to 6 units, therefore AB squared 6 squared, that is 36, plus AD squared. AD equals to 18 units, therefore AD squared is 18 squared, that is 324. In conclusion, we found out that according to the Pythagoras theorem, in the right triangle ABD, BD squared equals to 36 plus 324. So BD squared equals to 36 plus 324 is 360. In the next step, we'll substitute 360 by 36 times 10, so BD squared equals to 36 times 10. Here we take a root out of this equation. And we get that BD, that is the hypotenuse in right triangle ABD, equals to the square root of 36 times 10. Here we take 36 out of the root. The square root of 36 is 6. So BD is equal to 6. Inside the root we have to live with 10 times square root of 10 units. So here the hypotenuse BD of the right triangle ABD equals to 6 times square root of 10 units. In the next step, we calculate the area of triangle BDC. Repeat again, we calculate the area of the green triangle, triangle BDC. Here, the square bracket is the sign for the area. It means the area of triangle BDC. It will be equal to the base of the triangle times the height to the base over 2. Here I must emphasize that the height to the base must create 90 degrees with the base. So the area of triangle BDC, the green triangle BDC, will be equal to the base of the triangle. We will choose the base as BC. Times the height to the base over 2. Here we will extend side BC by a straight line. And from point D, we go perpendicular on the extended BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D and the extended BC as F. Actually, by doing this construction, we created a quadrilateral ABDF. This quadrilateral ABDF has 1, 2, 3 right angles. Therefore, this fourth angle must be also equal to 90 degrees. So actually inside quadrilateral ABDF we have 4 right angles, therefore quadrilateral ABDF is a rectangle. So I write it down. But we also know that the opposite sides of a rectangle are equal to each other. So here, side AB equals to side DF in rectangle ABDF. AB equals to DF. But it is given as the question that AB equals to 6 units. So I can write here that AB equals to 6. And from this equation, 6 equals to AB equals to DF. We will derive that DF it is also equals to 6 units. And DF is the height. The height to the base BC. So here DF, that is the height to the base, equals to 6 units. Now we can easily find out the area of the great triangle BDC. Here DF is the height to the extended BC. Why? Because it creates 90 degrees with the extended BC. Okay, this angle equals to 90 degrees. So the area of the great triangle, triangle BDC, will be equal to the base of the triangle. The base is BC. It is given as the question that BC equals to 13, so we'll substitute the base BC by 13 times the height to the base. We just right now found out that the height to the base is 6, all divided by 2. So in conclusion, we found out that the area of the great triangle BDC equals to 13 times 6 over 2. So the area of the great triangle BDC equals to 6 over 2 is 3, and 3 times 13 is 39. Okay, so the area of the great triangle BDC equals to 39 square units. In the next step, I will present to you a new rule. We'll implement a new rule in our original drawing. So this rule will be rule number 1. According to rule number 1, if triangle ABC, that will be any triangle, is blocked, or you can use the word blocked or inscribed, by a circle, then we actually can find out the radius of the circle that inscribes or blocks triangle ABC using a special formula. So first of all, I will draw the triangle and the circle. The center of this circle is at this point, point O. And inside this circle we have triangle ABC that is blocked or inscribed by this circle. This is triangle ABC. And the reason that we can say that this triangle ABC is blocked by this circle is because of the fact that all the three vertices of triangle ABC are touching the circle. This vertex of triangle ABC touches the circle at point A. This vertex of triangle ABC touches the circle at point B, and finally, this vertex touches the circle at point C. Only if all the three vertices of the triangle are touching the circle at different points, only then you can say that the triangle is blocked or inscribed by a circle. And here, this is an example of a triangle that is inscribed or blocked by a circle. We will define the radius of this circle as capital R. Here OM equals to capital R. According to our definition, we define the length of side AB of triangle ABC as A. Side BC equals to B units in its length, and side AC equals to C units in its length. Then the radius of this circle that blocks triangle ABC, that is to say capital R, will be equal to the multiplication of the side lengths of triangle ABC by each other, that is to say it is A times B times C, over 4 times the area of this triangle ABC, that is blocked by this circle. So whenever you have a triangle that is blocked or inscribed by a circle, we can find out the radius of the circle that blocks the triangle by using this formula. So if we know the side lengths of the triangle that is blocked by the circle, we can find out also the radius of the circle that blocks the triangle. Why? Because the area of the triangle can be calculated by knowing the side lengths of the triangle. So actually can implement this rule number 1 in our drawing. Why? Because in our drawing we have the green triangle BDC that is blocked by this circle. Why the green triangle is blocked by this circle? Because of the fact that this vertex of triangle BDC touches the circle at point B, this vertex touches the circle at point C, and this vertex touches the circle at point D. Therefore, we can definitely say that the green triangle BDC is blocked by this circle. So I write it down. The green triangle BDC is blocked or inscribed by the circle, and for that reason we can use rule number 1. Okay. We define the radius of this circle as capital R. Here, OM, that is the radius of this circle, equals to capital R according to our definition. So we can implement here rule number 1. According to rule number 1, the radius of the circle that blocks the green triangle BDC will be equal to the multiplication of the side lengths of the green triangle by each other. That is to say, it will be BC times CD times BD. Okay. The multiplication of the side lengths of the green triangle by each other over 4 times the area of the green triangle BDC. Okay. So the radius of this circle that blocks the green triangle BDC will be equal to BC equals to 13 units times CD equals to the square root of 61 units times BD equals to 6 times square root of 10 units, all divided by 4 times the area of this green triangle BDC. And we already found out that the area of the green triangle BDC equals to 39 square units. So actually, this expression is the answer to our question. Why? Because this is the area of the circle. We have to find out the radius of this circle. This is the radius of this circle. Capital R equals to the radius of this circle. Here we will just simplify this expression by dividing both the numerator and the denominator of this expression by 13. So the radius that we are looking for, capital R equals to 13 over 13 is 1, so 13 will get cancelled. In the numerator we left only with square root of 61 times square root of 10 times 6 over 4 times 39 over 13 is 3. So the radius of the circle equals to the square root of 61 units times the square root of 10 times 6 over 4 times 3 is 12, so in the denominator we left with 12. Here we will divide both the numerator and the denominator by 6, and we get that the radius that, of this circle, the radius that we are looking for, it is equal to the square root of 61 times the square root of 10. 6 over 6 is 1, so 6 will get cancelled. Over 12 over 6 is 2. Okay, so the radius of the circle equals to the square root of 61 times the square root of 10 over 2. Here we use the algebraic identity that states that the square root of a times the square root of b equals to the square root of a times b. According to this algebraic identity, we get that the square root of 61 times the square root of 10 is equal to the square root of 61 times 10, all divided by 2. So the radius of this circle, the radius that you are looking for, will be equal to either 61 times 10 is 610, so it is the square root of 610 over 2 units, or in terms of numbers, this expression equals to 12.349 units. This is the answer to our question. In the next step, I will present to you how to find out the radius of this circle according to the second method. In the second method, in the first step, we use all the things that we have already found out in the first method, so I will do it quickly. Here from point C, we will go perpendicular on AD. So this angle equals to 90 degrees. And this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and AD is E. Here in quadrilateral ABEC we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees also. So actually quadrilateral ABEC has 4 right angles, therefore quadrilateral ABC is a rectangle, and we know that the opposite sides of a rectangle are equal to each other, that is to say AB equals to EC. But AB equals to 6, therefore EC must be also equal to 6. According to the same rule that the opposite sides of a rectangle are equal to each other, we get that BC equals to AE. But BC equals to 13, therefore AE must be also equal to 13 units. Okay? And what is the length of line segment ED? It is easy to see from the drawing that ED equals to AD minus AE. AD is 18, AE is 13, so 18 minus 13 is 5. So ED equals to 5 units. So until now we did all the things in the first method. From now on, we will continue with the second method. And in the second method, from the center of the circle, that is to say from point O, we will do perpendicular on chord BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from the center of this circle, that is to say from point O and chord BC as capital N. And we define the touching point of the perpendicular from point O and AD as capital M. So in the next step, I will present to you a new rule. This will be actually rule number 2, and we will implement rule number 2 in our drawing. According to rule number 2, so we have a circle that could be any circle. The center of this circle is at this point O. Inside the circle we have chord BC. Chord BC could be any chord. And from the center of this circle, this is to say from point O, we do perpendicular on chord BC. So this angle equals to 90 degrees. And this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and chord BC as M. And rule number 2 states that a perpendicular from the center of a circle to any chord bisect the chord. So I write it down. A perpendicular from the center of the circle in our drawing, the center of the circle is at point O. Towards any chord here chord BC could be any chord, bisect the chord. So if perpendicular OM bisect chord BC, it means that BM equals to MC. Okay, so whenever we draw perpendicular from the center of a circle towards any chord, it will bisect the chord. In this case, perpendicular OM bisect chord BC, that is to say BM equals to MC. We actually can implement rule number 2 in our drawing. Why? Because in our drawing we have perpendicular ON to chord BC. In our original drawing we have perpendicular ON towards chord PC, and whenever you have a perpendicular towards the chord, it will bisect the chord. Bisect the chord according to rule number 2. So here perpendicular ON, that is from the center of the circle, that is to say from point O to chord BC, bisect chord BC. That is to say BN equals to NC. BN equals to NC according to rule number 2. In the next step, we will focus on quadrilateral ABMN. Inside quadrilateral ABMN, the upper quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So actually, inside quadrilateral ABMN, we have 4 right angles. Therefore, quadrilateral ABMN is a rectangle. I'll write it down. Quadrilateral ABMN is a rectangle because it has 4 right angles. This quadrilateral is a rectangle, but we also know that the opposite sides of a rectangle are equal to each other. That is to say, AM equals to BN. AM equals to BN. Likewise, in the next step, we will focus on the lower quadrilateral MNBC, MNEC. This quadrilateral. Inside quadrilateral MNEC, we have 1, 2, 3 right angles. Therefore, this fourth angle must be also equal to 90 degrees. So, I'll write it down. So actually I found out that inside the lower quadrilateral MNEC we have 4 right angles. And therefore quadrilateral MNEC is a rectangle. So I write it down. Quadrilateral MNEC is a rectangle. Because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, ME equals to NC. In rectangle MNEC, ME equals to NC. So to summarize what we did until now, we actually found out that according to rule number 2, BN equals to NC. And we also found out that according to the rule that the opposite sides of a rectangle are equal to each other, BN also equals to AM. So we can write here that BN equals to AM. And finally, according to the same rule that the opposite sides of a rectangle are equal to each other, we found out that NC equals to ME. So we can write here that NC equals to ME. And from this long equation, AN equals to BN equals to NC equals to ME, we will derive, here it is AM equals to BN, AM equals to BN. So from this long equation, AM equals to BN equals to NC equals to ME, we will derive that AM equals to ME. AM equals to ME. Side AM equals to side ME. Okay. In the next step, we will extend line segment DA until it touches the circle. We will define the touching point of the extended line segment DA and the circle as F. By doing this construction, we can here chord DF. Chord DF or chord FD. Okay? So here ON is perpendicular to BC according to our construction. Again, ON is perpendicular to BC. ON is a perpendicular, it is absolutely a straight line. ON is a straight line, and according to the old rule number 1, that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on the upper side of the straight line ON here at point M, the sum of the angles here must be equal to 180 degrees according to the old rule number 1. So which angles we have at the upper side of ON at point M? We have this angle that is equal to 90 degrees. Plus the missing angle, in total they must be equal to 180 degrees. So the missing angle must be equal to 90 degrees. Likewise, according to the same rule number 1, if we focus on the lower side of the straight line ON at point M, here the sum of the angles must be also equal to 180 degrees. So which angles we have at the lower side of ON at point M? We have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 180 degrees according to the old rule number 1. So the missing angle here must be equal to 90 degrees. So we found out here that OM is perpendicular to chord FD. Again, OM is perpendicular to chord FD. Why? Because this angle equals to 90 degrees and this angle equals to 90 degrees. So I write it down. Line segment OM is perpendicular to chord FD. And you should remember that line segment OM starts from the center of the circle and it is perpendicular to chord FD. Therefore, according to rule number 2, the perpendicular OM bisects chord FD. But the perpendicular OM bisects chord FD according to rule number 2. that is to say Fm equals to Md. Fm equals to Md. Fm equals to Md according to rule number 2. What is the value of Fm? Fm, from the drawing, it is very easy to see that Fm equals to Fa plus Am. Fa plus Am equals to Fm. So you can substitute Fm by Fa plus Am. And it is equal to Md. Here, Md equals to Me plus Ed. Again, Me plus Ed equals to Md. Okay, so substitute Md by Me plus Ed. In conclusion, we found out that Fa plus Am equals to Me plus Ed. But we have already found out that Am equals to Me. So those two line segments are equal to each other, therefore we can cancel them out. Okay, we'll cancel them, and we're left only with Fa that is equal to Ed. Fa equals to Ed. Fa equals to Ed. But we have already found out that Ed equals to 5 units, so we can write here that Ed equals to 5 units. And from this equation, Fa equals to Ed equals to 5, we will derive that Fa it is also equals to 5 units. Fa equals to 5 units. In the next step, we will extend side BA until it touches the circle. We will define the touching point of the extended side BA and the circle as P. So we have here chord FD that intersects with chord PB at point A. Chord FD intersects with chord PB at point A. Therefore, according to the old rule number 2, whenever you have two chords that intersect with each other, you can implement here the old rule number 2. According to the old rule number 2, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement the old rule number 2 in our drawing. So I write it down in our drawing. We have chord FD, that intersects with chord PB at point A. Repeat again. Now we're gonna drawing. We have chord FD that intersects with chord PB at point A. Okay, chord FD intersects with chord PB at point A. Therefore, according to the old rule number 2, we get that FA times AD equals to PA times AB. Okay, again, according to the old rule number 2, FA times AD equals to PA times AB. FA times AD equals to PA times AB. FA equals to 5 units. AD equals to 18 units. PA is the missing line segment, so we leave it as it is. And finally, AB equals to 6 units, so we substitute AB by 6. In conclusion, according to the old rule number 2, we found out that 5 times 18 equals to PA times 6. Here we divide this equation by 6, and we get that 5 times 18 over 6 equals to PA. Okay, so here 18 times 6 is 3, and 3 times 5 is 15. We actually found out that PA, the missing line segment, equals to 15 units. So I can write down in the drawing that PA equals to 15 units. So in the next step, I will present to you a new rule, and we will implement the new rule in our drawing. This new rule will be actually rule number 4. According to rule number 4, if you have a circle that could be any circle, the center of this circle is at this point that we define as point E. And we have chord AB, this is chord AB, that is perpendicular to chord CD. This is chord CD. The two chords are perpendicular to each other, that is to say they create between them at the intersection point 90 degrees. This angle equals to 90 degrees. We define the intersection point between the two chords as point O. Okay, so I write the rule down. If two chords are perpendicular to each other, then the certain formula is true. And we will define the radius of this circle as capital R. Here equals to capital R according to our definition. So we can write down that chord AB is perpendicular to chord AD. If chord AB, that could be any chord, is perpendicular to chord CD, and they are perpendicular to each other at the intersection point, that is to say, at this point O. At point O. So whenever you have two chords that are perpendicular to each other, we can use a certain formula in order to find out the radius of this circle that contains the chords. So if we have two chords that are perpendicular to each other, then the radius of this circle that contains the chord, that is to say 4 times r squared, will be equal to AO squared plus OB squared plus CO squared plus OD squared. So whenever you have two chords that are perpendicular to each other, then you can find out the radius of the circle that contains the two perpendicular chords by using this formula. Or this formula is true for two chords that are perpendicular to each other. By using this formula, we will find out the radius of this circle that contains the chord. And the radius of this circle is equal to capital R. So if chord AB is perpendicular to chord CD, and the intersection point, that is to say, at point O, that they are perpendicular to each other, then the following formula is true. 4r squared, or r is the radius of this circle, equals to AO squared plus OB squared plus CO squared plus OD squared. So we actually can implement rule number 4 in our drawing. Why? Because in our drawing we have also chord FD that is perpendicular to chord PB at point A. Why they are perpendicular to each other? Because of the fact that an intersection point, that is to say at point A, they create between them 90 degrees. Therefore they are perpendicular to each other, and for that reason you can implement here rule number 4. So I write it down. In our original drawing, chord FD is perpendicular to chord PB. And the two chords are perpendicular to each other at the intersection point at point A. Whenever you have two chords that are perpendicular to each other, you can implement in that circle rule number 4. Okay? So therefore, here we will define the radius of this circle as capital R. Here OM equals to capital R according to our definition. So here we can implement rule number 4 because we have chord FD that is perpendicular to chord PB. And according to rule number 4, we will get that 4r squared, r is the radius of this circle, r is the radius of the circle, equals to fa squared plus ad squared plus PA squared plus AB squared. I'll repeat again. Because of the fact that in our regular drawing chord of this perpendicular to chord PB, we can implement here rule number 4. According to rule number 4, 4r squared, r is the radius of this circle, equals to fa squared plus ad squared plus pa squared plus ab squared. 4r squared equals to fa squared plus ad squared plus pa squared plus ab squared. So 4r squared is equal to fa squared. Fa equals to 5 units, therefore fa squared equals to 5 squared, that is 25, plus ad squared. Ad equals to 18 units, therefore ad squared equals to 18 squared, that is 324, plus PA squared. PA equals to 15, therefore PA squared equals to 15 squared, that is 225, plus AB squared. AB equals to 6 units, therefore AB squared equals to 6 squared, that is 36. In conclusion, we found out that 4r squared, repeat again that r is the radius of the circle, equals to 25 plus 225 is 250, plus 324 plus 36 is 360. So 4r squared equals to 250 plus 360 is 610. So we found out that 4r squared equals to 610. Here we will divide this equation by 4 and we get that r squared equals to 610 over 4. Here we take a root out of this equation and we get that r equals to the square root of 610 over 4. That is to say r, the radius of this circle, the radius that we are looking for, it is equal to the square root of 610 and the square root of 4 is 2. In conclusion, we found out that the radius of this circle, the radius that we are looking for, OM, that is equal to capital R, it is equal to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. So we finish with the second method. In the next step, we'll summarize the lecture. We start with the first method. In the drawing we have a circle. We know that the center of this circle is at this point O. Line segment AB equals to 6 units. Line segment AD equals to 18 units. Line segment BC equals to 13 units. This angle BAD equals to 90 degrees. This angle ABC equals to 90 degrees. Our mission is to find out the radius of this circle. Here OM that is equal to capital R, according to our definition. So in the first step, from point C we draw perpendicular on AD. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. By doing this construction, we created here quadrilateral ABEC. Inside quadrilateral ABEC we have 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees. Therefore quadrilateral ABEC that has 4 right angles relate to it as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. This is to say AB equals to EC. But AB equals to 6 units, therefore EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that BC equals to AE. But BC equals to 13 units, therefore AE must be also equal to 13 units. Then what is the length of line segment ED? ED equals to AD minus AE. This is to say it is equal to 18 minus 13, this is 5. Then we join points C and D together by a straight line. In this way we created the green right triangle, triangle ECD, and then implemented the Pythagoras theorem on the green right small triangle, triangle ECD. In the green small right triangle, triangle ECD, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is DC or CD, therefore the square of the hypotenuse is CD square or DC square, and it must be equal to the sum of the squares of the perpendiculars. This is to say it must be equal to EC square plus ED square. Okay, so DC square equals to EC square plus ED square. So DC square, that is the square of the hypotenuse, equals to EC square. EC equals to 6, therefore EC square is 6 square. This is 36 plus ED square. ED is 5, therefore ED square is 5 square, that is 25. In conclusion, further, the DC square equals to 36 plus 25. 36 plus 25 is 61. So DC square equals to 61. Here we took a root out of this equation and found out that DC equals to the square root of 61 units. Here, DC, the hypotenuse DC equals to the square root of 61 units. In the next step, we join points B and D together by a straight line. By joining points B and D, we created the right triangle ABD. Then we implemented the Pythagoras theorem on the right triangle, triangle ABD. Okay, yeah. We have here triangle ABD, so according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is BD in the right triangle ABD, therefore the square of the hypotenuse is BD square. And it must be equal to the sum of the squares of the perpendiculars. That is to say it must be equal to AB square plus AD square. Repeat again. In the right triangle ABD, BD square must be equal to AB square plus AD square. Here AB equals to 6, therefore AB square is 6 square, that is 36. So BD square, that is equal to AB square, it is 36 plus AD square. Here AD equals to 18 units, therefore AD square equals to 18 square, that is 324. In conclusion, we found out that BD square equals to 36 plus 324. 36 plus 324 is 360, so BD square equals to 360. Then we substituted 360 by 36 times 10, and then so BD square equals to 36 times 10. Then we took a root out of this equation, and we found out that BD equals to the square root of 36 times 10. Here we took 36 out of the root. Why? Because the square root of 36 is 6. So BD equals to 6, inside the root we left only with 10. So we found out that the hypotenuse BD of the right triangle ABD equals to 6 times square root of 10 units. Here, BD equals to 6 times square root of 10 units. Now we found out the area of the green triangle, triangle BDC. The area of any triangle, and especially the area of triangle BDC, it is equal to the base times the height to the base over 2. Here the square brackets is the size of the area, it is the area of triangle BDC. Here I must emphasize that the eye to the base must create 90 degrees with the base. Okay. So the area of this triangle, the great triangle BDC, equals to the base of the triangle times the eye to the base over 2. We prove the base as BC, so we substitute the base by BC, so it is the base times the height over 2. In order to find out the height, we extended side BC by a straight line, and from point D, we draw perpendicular on the extended BC. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. By doing this construction, we created a quadrilateral ABDF. Inside quadrilateral ABDF, we have 1, 2, 3 right angles. Therefore, this fourth angle must be also equal to 90 degrees, and therefore quadrilateral ABDF is 4 right angles, and therefore quadrilateral ABDF is a rectangle. Quadrilateral ABDF is a rectangle because it has 4 right angles, and we know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side DF. Side AB equals to side DF. And it is given as the equation that AB equals to 6, so we can write here that AB equals to 6, and from this equation 6 equals to AB equals to DF, we will derive the DF, it is also equals to 6 units. But DF, it is the height to the base. Why? Because DF creates 90 degrees with the extended base BC, therefore DF is the height to the base. So the height of the great triangle DBC equals to 6 units. Now we can easily find out the area of the great triangle BDC. The area of the great triangle BDC equals to the base of the triangle. The base of the triangle is BC, and BC equals to 13 units. Therefore, we can substitute BC by 13 times the height. We just right now found out that the height to the base equals to 6 units over 2. So the area of the great triangle BDC equals to 13 times 6 over 2. 6 over 2 is 3, and 3 times 13 is 39. In conclusion, we found out that the area of the great triangle BDC equals to 39 square units. Okay? In the next step, I actually presented to you a new rule number 1, and implemented rule number 1 in our drawing. According to rule number 1, if triangle ABC, this is triangle ABC, this could be any triangle, is blocked or inscribed by a circle, you can see here that this circle blocks triangle ABC, then the following formula will be true. So whenever you have a triangle that is inscribed or blocked by a circle, then you can find out the radius of this circle that blocks the triangle by using this formula. Here side AB equals to A units in its length, side BC equals to B units in its length, and side AC equals to C units in its length. Okay? So, the definition of a triangle that is blocked by a circle is that all the 3 vertices of the triangle are touching the circle, like in this drawing. We define the radius of this circle as capital R, therefore the radius of this circle will be equal to A times B times C, that is the multiplication of the side lengths of the triangle by each other, over 4 times the area of this triangle ABC, that is blocked by the circle. So we can actually implement rule number 1 in our drawing. Why? Because in our drawing we have the great triangle BDC. You can see that all the 3 vertices are touching the circle at different points. This vertex of triangle BDC touches the circle at point B. This vertex touches the circle at point C, and this vertex touches the circle at point D. Therefore, we can definitely say that the green triangle BDC is blocked by this circle, And for that reason, you can implement here rule number 1. So I repeat again that the green triangle BDC is indeed blocked by the circle. Therefore, according to rule number 1, we get that the radius, we define the radius of this circle as capital R, or M equals to capital R. It is equal to, according to the formula, it is equal to the multiplication of the side lengths of triangle BDC by each other. That is to say, it is BC times CD times BD, BC times CD times BD, over 4 times the area of the green triangle BDC. The length of side BC is 13 units, the length of side CD is square root of 61 units, and the length of side BD is 6 times square root of 10 units. Okay? Over 4 times the area of the green triangle BDC, and we have already found out that the area of the green triangle BDC equals to 39 square units. So actually, this expression is the answer to the question. Why? Because we asked to find the radius of this circle, and the radius of this circle is capital R, and capital R, the value of capital R is equal to this expression. In the next step, we just simplified this expression. That is to say, we divided both the numerator and the denominator of this expression by 13. Here, 13 over 13 is 1, so in the numerator, we left only with the square root of 61 times square root of 10 times 6. We have to divide also the denominator by 13. In the denominator, we have 4 times 39. 39 over 14 is 3. So in total, in the denominator, we left only with 4 times 3, that is 18. 12. 4 times 3 is 12. In the denominator, we have square root of 61 times square root of 10 times 6. Okay? So here we divided both the numerator and the denominator by 6. 6 over 6 is 1, so 6 will get cancelled. In the numerator, we left only with square root of 61 times square root of 10. 12 over 6 is 2. So the radius of the circle equals to the square root of 61 times square root of 10 over 2. Here we have the algebraic identity that the square root of A times square root of B equals to the square root of A times B. According to this algebraic identity, we will get that the square root of 61 times the square root of 10 equals to the square root of 61 times 10, all divided by 2. 61 times 10 is 610. So we have that the radius of this circle capital R equals to the square root of 61 over 2 units, or in terms of numbers, the radius of this circle capital R equals to 12.349 units. We finish with the first method. Then I presented you how to find out the radius of this circle according to the second method. In the second method, in the first step, we used with all the things that we already used in this first method. So I repeat on it quickly. From point C, we drew perpendicular on AD. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD as E. By doing this construction, we created quadrilateral ABEC. Quadrilateral ABEC, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees, therefore quadrilateral ABEC has 4 right angles, therefore quadrilateral ABEC is a rectangle. And we know that the opposite sides of a rectangle are equal to each other, that is to say AB equals to EC. but AB equals to 6 units, therefore EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that BC equals to AE, but BC equals to 13 units, therefore AE must be also equal to 13 units. What is the length of line segment ED? ED equals to AD minus AE, that is to say it is 18 minus 13, that is 5. So until this stage, we did all the things that we done here in the first method. From now on, we continue with the second method. That is to say, in the second method, from point O, that is the center of this circle, we draw perpendicular on chord BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O to chord BC as capital N, and we define the touching point of the perpendicular from point O and AD as capital M. Then I presented to you a new rule number 2, and we implemented rule number 2 in our drawing. According to rule number 2, whenever you have a perpendicular from the center of the circle towards any chord, it will bisect the chord. The center of the circle is at this point, point O. We have perpendicular OM to chord BC. That is to say, this angle equals 90 degrees and this angle equals 90 degrees according to our construction. According to this rule number 2, it will bisect chord BC. Perpendicular OM bisect chord BC. That is to say, BM equals to MC. Okay, BM equals to MC according to rule number 2. We actually can implement rule number 2 in our drawing. Why? Because in our drawing, the center of this circle is at this point, point O, and from the center of this circle, that is to say from point O, we have perpendicular ON to chord BC. And whenever we have a perpendicular towards any chord, it will bisect the chord. So perpendicular ON will bisect chord BC. That is to say BN equals to NC. Okay? I'll repeat again. Perpendicular ON from the center of the circle to chord BC bisects the chord. Okay, perpendicular ON bisects chord BC, that is to say BN equals to NC. BN equals to NC according to rule number 2. Okay, then we focused on quadrangle ABMN. Inside quadrangle ABMN, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees, therefore quadrangle ABMN that has 4 right angles will relate to it as a rectangle. Okay, here quadrangle ABMN is a rectangle because it has 4 right angles, and we also know that the opposite sides of a rectangle are equal to each other, that is to say AM equals to BN. AM equals to BN. Likewise, we focused on the lower quadrangle MNEC. In this quadrangle, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Therefore, quadrangle MNEC that has 4 right angles, it is a rectangle. Quadrangle MNEC is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, ME equals to NC. ME equals to NC. ME equals to NC. So we can summarize what we did until now. We found out that according to rule number 2, BN equals to NC. And according to the rule that the opposite sides of a rectangle are equal to each other, we found out that BN equals to AM. So we can write here that BN equals to AM. According to the same rule that the opposite sides of a rectangle are equal to each other, we found out that NC equals to ME. So we can write here that NC equals to ME. And from this long equation, AM equals to BN equals to NC equals to ME, we will derive that AM equals to ME. AM equals to ME. Here. Side AM equals to side ME. Okay. In the next step, we extended line segment DA until it touches the circle at point F. Okay. ON is perpendicular to chord CB. ON is a perpendicular that is absolutely a straight line. And according to rule number 1, that the sum of the angles from one side of a straight line is equal to 180 degrees. So we will focus on the straight line ON, on the upper side of the straight line ON at point M. Here the sum of the angles according to rule number 1 must be equal to 180 degrees. So which angles we have at the upper side of ON at point M? We have this angle that is equal to 90 degrees. Plus the missing angle, in total they must be equal to 180 degrees according to rule number 1. Therefore this missing angle must be equal to 90 degrees. Likewise, according to the same rule, rule number 1, if we focus on the lower side of the straight line ON at point M, here the sum of the angles must be also equal to 180 degrees. So which angles we have at the lower side of ON at point M? We have this angle that is equal to 90 degrees. Plus the missing angle, in total they must be equal to 180 degrees according to rule number 1. Therefore this missing angle must be equal to 90 degrees. Okay, so this angle equals to 90 degrees and this angle equals to 90 degrees. Therefore, line segment OM is perpendicular to chord FD. Line segment OM is perpendicular to chord FD. Repeat again. OM is perpendicular to chord FB. And line segment OM exits from the center of the circle, that is to say from point O. And whenever you have from the center of the circle perpendicular to any chord, it will bisect the chord according to rule number 2. That is to say, OM will bisect chord FD. If OM bisects chord FD, it means that FM equals to MD. Okay? FM equals to MD according to rule number 2. FM equals to MD. But FM, here, FM, it is equal to FA plus AM. FA plus AM equals to FM. So we can substitute FM by FA plus AM. And it is equal to MD. MD, here, MD equals to ME plus ED. ME plus ED equals to MD. So we can substitute MD by ME plus ED. In conclusion, we found out that FA plus AM equals to ME plus ED. But we have already found out that AM equals to ME. AM equals to ME. And because of the fact that those two line segments are equal to each other, we can cancel them out of the equation. So we cancel them and we left only with FA that is equal to ED. FA equals to ED. FA equals to ED. But we have already found out that ED equals to 5 units. So we can write here that ED equals to 5 units. And from this equation FA equals to ED equals to 5, we will derive that FA equals to 5 units. Here, FA equals to 5 units. In the next step, we actually extended side BA until it touches the circle at point P. So here we have chord FD that intersects with chord PB at point A. And whenever you have two chords that intersect with each other, you can implement the old rule, rule number 2. The old rule, rule number 2 states that if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So actually you can implement here rule number 2. because of the fact that chord FD intersects with chord PB at point A, we can implement here on number 2. Here chord FD intersects with chord PB at point A. And according to rule number 2, FA times AD equals to PA times AB. Again, FA times AD equals to PA times AB. FA times AD equals to PA times AB according to the old rule, rule number 2. Okay? FA equals to 5 units. AD equals to 18 units. PA is the missing line segment, so we leave it as it is. And finally, AB equals to 6 units, so we substitute AB by 6. And we found out that 5 times 18 equals to PA times 6. Here we divided this equation by 6, and we found out that PA, the missing line segment, equals to 5 times 18 over 6. 18 over 6 is 3, and 3 times 5 is 15. So in conclusion, we found out that the missing line segment PA, equals to 15 units in its length. Then I presented to you rule number 4, and we implemented rule number 4 in our drawing. According to rule number 4, whenever you have two chords that are perpendicular to each other, then a certain formula is true. This formula is true. We defined the center of this circle, the radius of this circle, the center of this circle is at point E. Therefore, the radius of this circle, EM, equals to capital R. So we can find out the radius of this circle according to this formula whenever you have two chords that are perpendicular to each other. And indeed here we have chord AB that is perpendicular to chord CD at point O. This angle equals to 90 degrees, therefore the two chords are perpendicular to each other, and therefore we can implement here rule number 4. According to rule number 4, here, if the radius of this circle is capital R, then 4R squared equals to AO squared plus OB squared plus CO squared plus OD squared. Again, 4R squared, R is the radius of this circle, equals to AO squared plus OB squared plus CO squared plus OD squared. Okay? So we actually can implement rule number 4 in our drawing. Why? Because in our drawing we also have two chords that are perpendicular to each other. Here chord FD is perpendicular to chord PB at point A. Here the create between them 90 degrees at the intersection point A. And because of the fact that whenever you have two chords that are perpendicular to each other, you can implement rule number 4. Therefore, in our drawing we can also implement rule number 4. Because of chord FD is perpendicular to chord PB at point A. I'll repeat again, chord FD is perpendicular to chord PB at point A, therefore we can implement here rule number 4. According to rule number 4, if we define the radius of this circle as capital R, that is to say OM equals to capital R, then the following formula will be true, that 4R squared equals to FA squared plus AD squared plus PA squared plus AB squared. I'll repeat again. 4R squared equals to FA squared plus AD squared plus PA squared plus AB squared according to rule number 4. So 4R squared, R is the radius of the circle, equals to FA squared. FA equals to 5, therefore FA squared is 5 squared, that is 25, plus AD squared. AD is 18 units, therefore AD squared is 18 squared, that is 324. Plus PA squared. PA equals to 15 units inside, therefore PA squared equals to 15 squared, that is 225. Plus AB squared. AB equals to 6 units, therefore AB squared is 6 squared, that is 36. So in conclusion, we found out that 4R squared equals to 25 plus 225 is 250. And 324 plus 36 is 360. So 4R squared equals to 250 plus 360, and 250 plus 360 is 610. So we found out that 4R squared equals to 610. We divided this equation by 4 and found out that R squared equals to 610 over 4. Here we took a root out of this equation and we found out that the radius of this circle OM the radius that we are looking for, it is equal to either here, the square root of 610 over 4. So the radius of the circle equals to the square root of 610, and the square root of 4 is 2. So in conclusion, we found out that the radius of this circle, that is to say capital R, it is equal to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. Okay, thank you very much.